Hello, today we will prove that Pell's equation will always have a positive integer solutions if d is not a perfect square, and Pell's equation is that x squared minus dy squared equals 1. To prove this, we need to use several lemmas. The first one is that we can always find t1 and w1 such that partial part of t1 minus w1 squared d will be less or equal to 1 over c1 for every positive number c1, and w1 must be less or equal to c1. To prove this, let's divide the positive axis into several parts. This must be 1 over c1, this 2 over c1, up to c over c1, and look at the partial parts of square root d, 2 times square root d, and c1 square root d. It is clear that none of them must be here, otherwise we can find some t1 such that t1 minus w1 square root d will have absolute value less or equal to 1 over c1. So we can get two integers k and m by Dirichlet's theorem that k square root d and m square root d will be in the same segment. Both of them must be in the same region. If we take like t2 and t3 in this case, we get that t2 minus k, t2 minus t3 minus k minus m squared d. This number has absolute value less or equal to 1 over c1. And what do we know about k minus m and t2 minus t3? Both of these integers must be less than c1. This number is less than c1. And we don't need any information about t2 and t3. And why do we need this lemma? The main reason is that if we discuss, call this t1 and call this w1. Now let's discuss t1 square minus w1 square d. This clearly equals t1 minus w1d times t1 plus w1 square d. Because of our lemma, we know that t1 minus w1d, this number is less or equal to 1 over c1. And what do we know about this number? This number must be less or equal to 2 times w square root d plus 1, because the difference between t1 and wd must be at most 1. So we can assume that 2 times wd plus 1, square wd plus 1, must be greater than this number. So their product must be less than 2 times w times square root d over c1 plus 1 over c1. And by using the fact that w1 is less or equal to c1, we can also see that this number is less or equal to 2 times square root d plus 1. Now we can take another number, c2, such that absolute value of t1 minus w1 square root d, this is more than 1 over c2. By the same logic and same arguments, we can find another numbers, t2 and w2, such that w2 will be less or equal to c2, and absolute value of t2 minus w2 squared d will be less or equal to 1 over c2. And in the similar logic, we will see that t2 squared minus w2 squared d will be less or equal 2 times square root d plus 1. This absolute value of this one. So if we do this process infinitely many times, we will generate numbers t1, w1, t2, w2, up to t and wn, where we know that all of these numbers, ti square minus wi square d, must be in the region from negative square root d square root 2 times d minus 1 and positive square root d plus 1. Because we know that we can generate infinitely many such pairs, there will exist number k such that tm square minus wm squared square root d will be equal to k for infinitely many numbers of tm and wm, and call this new sequence q1 w1 q1 d1, then q2 d2, and up to q big N dn. Because we know that this n can go to infinity, there will exist two pairs who will have the same remainders modulo k. And let's assume that qi equals qj mod k and di equals dj mod k. Now we are also using Dirichlet's theorem, and from this point we need to generate new number t0 and w0, which will be depend only qi and qj. t0 will be qi times qj minus d times di times dj, and w0 must be qi times dj minus qj times di. If we look at t0 square minus dw0 square, we get that this number equals k square. Now we need to look at these numbers, t0 and w0. We will show that both of these numbers must be divisible by k. And if this is correct, we can divide both of these numbers, t0 and w0, by k, and we get 1. Now let's see what will be. t0 equals qi times qj minus d times di times dj. Now we can use the fact that qi equals qj mod k and di equals dj mod k. So this equals qi square minus d times di square mod k. And clearly this is 0 because this equals k. So this is 0. Now we have proved that t0 equals 0 mod k. Similarly, we get that w0 equals qi times dj minus qj times di, because we know that these two numbers are equal mod k and these two numbers are also equal mod k. Their difference will be 0 mod k. So we have proved that t0 and w0, both of these numbers are multiple of k. So we can write t0 equals k times something, or t0 prime, and w0 equals k times w0 prime. And in this case, if we insert in this equation k square times t0 prime square minus d times k square times w0 prime square equals k square, and if we cancel out k squares, we get that t0 prime square minus d times w0 prime square equals 1. So we have found two integers, t0 prime and w0 prime, which will give us the exact formula which we need for Pell's equation to prove that there exist two integers, two positive integers, t0 prime and w0 prime, such that t0 prime square minus w0 prime square have the property that their difference equals 1 if we multiply w0 square by d. This was all I want to discuss for today. If you want to discuss or consider some theorems, please write in the comments. Oh, and don't forget to like and subscribe.